I just wanted to first start out by highlighting some of the interesting applications of calculus we've treated so far in the course. So we did drone position from IMU acceleration, and also at the same time squeezed in a little intro to the Kalman filter, something that will become very important to you as you move on and do navigation and planning for your robots. We did two properties that are required for understanding robot links: their center of mass and the moment of inertia about the z-axis. We did arc length, which also is called path length, to help you understand how far a robot has traveled. Even if the path is extremely complicated, we saw that we could use the Pythagorean theorem to actually derive a formula that was very easy to integrate. We didn't spend much time on roots of functions from Rn to Rn, though we reviewed it quickly. It's covered primarily in Rob 101. But we spent much more time on gradient descent, even though it's introduced in Rob 101. We needed to get down to the nitty-gritty of the geometry of how you choose a step direction, delta x. And so by linearizing the cost function with the gradient and linearizing the constraints, equality constraints, via the gradient as well, we found a set of linear equations that need to be satisfied by the step direction, that its dot product with the gradient of the cost should be negative to decrease the cost, and the step direction should be orthogonal to the gradients of the constraints so that the constraints stay relatively constant. We moved on from there to Lagrangian dynamics. Now we did it for planar bodies of point masses connected by links with revolute joints. So that covers robot arms and legs and many other interesting things. And the amazing part is, if you understand two quantities, the potential energy, PE, and the kinetic energy, KE, then by this magic thing called Lagrange's equation, you can generate a set of differential equations that describe the motion of the object. And what's cool about potential energy, at least for point masses, it's just the point mass times the gravitational constant times the height above a reference height. So you have to set a reference. And then to get the kinetic energy, you simply differentiate the positions of the point masses. And to do that, you use the chain rule and the total derivative in any symbolic package. You generate those very quickly. Then the kinetic energy is 1/2 m norm of the velocity squared. So it's the x component squared plus the y component squared of the velocity. And from that, from something that's relatively easy to compute, then it's just a bunch of derivatives to get the full differential equations. And these are a generalization of Newton's F equals ma, or ma equals F, where here's the m, the mass inertia matrix, here's the a, the acceleration of the generalized position coordinates. These are things dealing with rotating bodies that don't show up in the standard Newton equations, okay? So, and then this is the effects of gravity or potential energy from springs, and then this would be motors or rockets or whatever external forces you have acting on the body. We looked at an application of gradient descent to path planning using radial basis functions. Once again, made contact with Rob 101. And then as a very last thing, we noted that we could numerically integrate the robot equations We haven't defined yet what is a solution to a differential equation. We'll do that in chapter 9. But we applied the same numerical integration we did for drones from project 1 to a two-link pendulum, and the motion looked just like what we'd expect from a two-link pendulum. So we've done a lot, and it's half the term. So I hope it's felt worthwhile. I know a lot of the material for many of you has been reviewed because you had Math 115 and 116, but I challenge you to find most of these applications in your Math 115 and 116 courses. And I hope you come and show me that I'm wrong, and that the math department has been doing it all perfectly right all along, okay? That would be great news. So we just got started at the very end of Wednesday by stating that we're going to start moving into chapter 7 with title Antiderivatives and the Fundamental Theorems of Calculus. And we defined an antiderivative. So it's the opposite of differentiation. Capital F is an antiderivative of little f if the derivative of capital F equals f. So you can take a function, you can take its first derivative, its second derivative, its zeroth, its third derivative. Sometimes the function itself is called the zeroth derivative. And the antiderivative is like the -1 derivative. And then you could do the antiderivative of that, the -2 derivatives. You got a whole tower of these things. You start out with a function, you can differentiate it, or you can anti-differentiate it. So we'll get started on that. Questions, comments, protests? Everybody enjoying the extra sunshine? I mean, that's the only downside of our lack of sleep this morning. Lack of sleep is the downside, excuse me, but we do get a little bit extra sun. And I think when we walk out of here at 6:20, we can actually see the way to our cars, okay, or the bus. Amazing. Okay, notation. So for the antiderivative, you write it as f of x dx, or sometimes you'll put in another dummy variable in here. But the key thing is there are no limits shown. No limits, okay? That's the sign that you're computing an antiderivative. So we have 3 types of integrals so far. We started out with our definite Riemann integral. And then A and B are fixed numbers, like 3 to 27 f of x dx. And so that produces a number. We have indefinite integrals. So we put a variable in the limits. And this produces a function because we vary x, the area under the interval from a to x varies. And then we have the antiderivative. No limits. And it's also a function because by definition, the antiderivative is a function, capital F of x, whose derivative is equal to what's under the integral, okay, which is called the integrand. It's the same for all of these. That's called the integrand, what's under the integral sign. Okay, so definite integrals produces a number, indefinite, a function of either the upper limit as I'm showing, or it could be the lower limit, it doesn't matter, and an antiderivative has no limits whatsoever. Okay, so I'm going to give you 3 functions, and I want you to determine if some of them are antiderivatives of others. So f sub a of x is equal to x times the natural logarithm of x minus x f sub b of x is equal to the natural logarithm of x. F sub c, natural logarithm of x squared. Determine if any of f a, f b, f c is an antiderivative of one of. Okay, so that's our challenge. So how do you show one thing is an antiderivative of another? You apply the definition. So you need to differentiate these functions and see if they equal one of the other functions in the list. It's that simple. So how do you check if something is an antiderivative? You simply differentiate it. Okay? Let me know what you get for these guys, okay? Who's feeling strong in the chain rule and the product rule? Okay, Jason's got it going. Yep, and Jason, you are correct. Okay, so we got one answer. That'll encourage me to get going. So look, we differentiate x, we get 1, so this is logarithm. So it's the derivative of the first one times the second one, minus x times the derivative of log of x, which is 1 over x, and then minus, then minus 1. And those two things cancel, and this equals fb of x. Hence, fa is an antiderivative of FB. You anti-differentiate the log and you get FA. So, okay, so we have FA of x prime equals FB of x, and that's if and only if FA of x is an antiderivative whoops. Okay, so FB is the derivative of FA. That makes FA the antiderivative of FB. So we're just warming up, practicing definitions here. Okay, derivative log of x, 1 over x, and it's not equal to anything on our list. So FB is not the antiderivative of any function in our very small list. And then by log properties, even though this thing looks complicated, that's 2 times the natural log of x. Hence the derivative is just 2 over x. And it's not, and so these are not antiderivatives of functions in our list. They're antiderivatives of something else, okay? So not anti-Ds of anything in our list. Okay, so the bottom line, if somebody proposes an antiderivative to you, you have a very simple test. Differentiate it. Does it equal the function it's supposed to be the antiderivative of? You're done. Okay, so to test, wrong consonant. In other words, apply the definition. Okay, so that's all you have to do. Okay, so that's what antiderivatives do. I'm going to plug in a little table, and then we're going to use it a couple of times, so we might stick it back in again. This table consists of all of the antiderivatives that I have had memorized for my entire calculus career, probably the ones that most of you have memorized as well. So how does this work? Before we had functions, and we calculate their derivative. So the derivative of a constant is 0. The derivative of a monomial, you bring the power down and decrease by 1, etc. Exponential is its own derivative. But because if I start with the bottom row, anything in the top row I differentiate, I get the bottom row. That makes the top row an antiderivative if I think of the bottom row as the given function. So those things are dual. Okay? Function derivative is the same thing as having function on the bottom and antiderivative on the top. So who's the function and who's the derivative or the antiderivative? It's your call, okay? And we'll check a few of these. So sine to cosine, cosine to minus sine, tangent to 1 plus tangent squared. So tangent to 1 plus tangent squared is applying the quotient rule to sine of x over cosine of x. And if you have it memorized as the derivative of tangent is secant squared, That's the same thing. So it's up to you. I always use 1 plus tangent squared. Okay, so that's the relationship between functions and antiderivatives. And if you want to check if tangent is an antiderivative of 1 plus tangent squared, you simply differentiate tangent, produce 1 plus tangent squared with the quotient rule, and you are done. That's how it is. Now, why do I have these constants C up there? And it's simply because if f of x is an antiderivative if capital F of x is an antiderivative of lowercase f of x, then f of x plus c is also an antiderivative for any constant c. I think I'm leaving out letters here. And we'll typically take our constant c's to be real numbers, but in theory, they could be complex numbers. It doesn't really matter. And why is this true? It's because if I do d by dx of f of x plus c, that's f prime of x plus c prime. That's 0. So it equals f prime of x, and it equals, that's f of x, because f was an antiderivative. Capital F was an antiderivative of lowercase f. So just because the derivative of a constant is 0. And then it's essentially a corollary of the fact if capital F of x and capital G of x are both antiderivatives of little f of f, then f of x minus g of x equals a constant. Okay, so the two functions differ by a constant. And f of x, if I differentiate it, I get f prime minus g prime. It's an antiderivative of little f. It's an antiderivative of little f. So that's 0. And then if I put a constant, that's pretty much it. Okay, so any two antiderivatives of a function are identical up to an arbitrary constant. And that's why we had these constants up here. And it can't be a more complicated function like c of x, because c prime of x then would not be 0, and the two things would not be antiderivatives of the same function. Okay, so verifying that something is an antiderivative is very easy. You just compute it. So if someone gives you the candidate, that's really easy. But finding a candidate when it's not given to you, candidate antiderivative, and it's a fact that it is generally impossible to find one within the class of elementary functions. And we said like 3 words about this on Wednesday or whatever, 10 days ago, 12 days ago. Elementary functions, those are things you build from sine and cosine, exponentials and logs, powers and radicals, and compositions of all of those operations. So you can build up these tremendously complex functions, okay? And the set of all of those are called elementary functions. And the thing is, if a function is elementary, its derivative is also elementary. But if a function is elementary, its antiderivative does not have to be. Okay. And I think you can prove that the set of, if you define a measure in some general way of how to calculate volume, the set of elementary functions within the set of differentiable functions is really thin. It would have volume 0. So you'd have if you just grab an arbitrary elementary function, the probability of it having an antiderivative that is elementary is 0. Now, what you were taught in Math 116 was a whole bunch of rules to compute antiderivatives of elementary functions when the antiderivative itself is also elementary. Okay? Guess what? You solved 0% of all the integral problems in the world. How do you feel about that? You worked hard, didn't you? So, this is why I do antiderivatives late in the course, because the way to really think about integrals, numerical. And that's what all real engineers do, because the problem that's going to be given to you in your first really meaningful internship or that first job you get and you've got to integrate something, it will not have an antiderivative. Okay, it just will not. So, sad fact. I'm sorry to break your heart that you spent all that time learning tables of integrals and they're not going to help you very much. So. Okay, so let's move on, nevertheless, to the fundamental theorems of calculus, because they're super cool. We'll state both of them. One of them says that every continuous function has an antiderivative. You just can't compute it, but it does exist. You can't compute it analytically. You can compute it numerically, okay? And the other one says every definite integral can be solved via antiderivatives. Okay, so these are the fundamental things that you learn about calculus. They tie differentiation and integration together as inverse operations. First FTC, first fundamental theorem of calculus. And it says, every continuous function has an antiderivative. Okay, so if you give me little f, big F is sitting out there as long as little f is continuous. Does not say you can compute it in closed form. It's a good thing it doesn't say that because it's false. Okay, so anyway, that's the first fundamental theorem of calculus. I'll write it down more precisely, but that's what it says. Every continuous function has an antiderivative. So if we wanted to be more precise, suppose f takes an interval ab to the reals, is continuous. And since we're not saying continuity at a point, we really mean it's continuous on the entire interval AB. And that means we pick an arbitrary point in the interior, the limit from the left is the limit from the right is equal to the value of the function. And at the two endpoints on A, the limit from the right is equal to the value of the function, and the limit from the left at B is equal to the value of the function. All those things exist. Then capital F takes AB to R defined by capital F is by definition equal to, let me let you catch up. Okay, we define it as the indefinite integral from a to x, f of y dy, for x's in the domain of definition of the functions. Okay, because the function is continuous, AB is bounded, x is in there, so AX is bounded, that Riemann integral exists. So there's no doubt about that Riemann integral. So you can always assign a value to it. Okay, so f of x is a well-defined function. Moreover, it's continuous. On AB. Differentiable on the open interval AB, and where it's differentiable, meaning for all x that is strictly greater than A and less than B, f prime of x is equal to f of x. So it is an antiderivative. Okay. And then you will also see this written as, no, I'm going to emphasize this, the derivative d by dx of the integral from a to x f of y dy equals f of x. All right, so this is the antiderivative. So f prime of x is equal, a big X is equal to f little x. To underline that differentiation is the inverse of integration. Differentiation is the inverse of integration. Okay, area, slope, they're related by one is the inverse of the other. You undo integration by differentiation. Cool? Pretty cool. So all of these antiderivative, every continuous function has an antiderivative. So it's just that unfortunately you can write down many elementary functions that are continuous, they have antiderivatives, but the antiderivative is not elementary, and so it uses things like Bessel functions and elliptical integrals and all these things that are somewhat complicated. Now here's something cool. Project 1. You guys did this. P at time t sub k plus 1 was equal to P at time tk plus the integral from t sub k to t subscript k plus 1 velocity, just using a dummy variable, tau. Okay. And so what you were doing was a numerical evaluation of the antiderivative of v of t for all times in t1, t2, up to some finite set tn. Okay, so in project 1, you were numerically computing antiderivatives. And since you didn't care how complicated that velocity signal was, you just applied Simpson's rule or trapezoidal rule or quad GK, okay, and you did the integral, and you were numerically evaluating an antiderivative. So you can always numerically evaluate these things, and that's what real engineers mostly have to do. If we can find these things, think of a more complicated function than the ones I have in this list, and we can find the antiderivative, we're usually very happy about that because, as the second fundamental theorem of calculus tells us, it makes it easier to evaluate a definite integral in closed form, and it's faster if we have it. But the sad thing is, normally, this is what we're stuck doing. It's not because we're conceited or we're dumb and we can't find antiderivatives, just that they don't exist in the class of elementary functions, and so you've got to go create these crazy oddball things. Questions? The idea clear? Every function has an antiderivative as long as it's continuous. And if it's piecewise continuous, break it up into the intervals over which it's continuous and find antiderivatives on those things and piece it together. Yes?
How would the equation behind the antiderivative make fractal function work? Because at every point you can keep going deeper, and then at a given point, the antiderivative function would need to have a derivative of every value. Would that make sense, or is it
No, it makes total sense. And then if you really wanted to compute derivatives, to go backwards, I'm going to use red because red is the antiderivative for the fun of it. So you've computed the antiderivative here. Interpolate, and then differentiate the interpolated function. So use regression like you were taught in Rob 101, and use any class of functions you want, RBF, monomials, sines and cosines, and then you differentiate those. And it's actually a very powerful way to compute derivatives from encoder data, which is discrete in time. So, yeah. So, we engineers, but also the numerical analysts in mathematics are very good at this kind of stuff too. And then they give you bounds for how accurate you are that are tighter than most things we know how to compute. Okay, so they've got some power. Okay, there's no doubt about it. But this is typically what we have to do. Other questions? So we're just trying to understand the conceptual boundaries of what we can compute and expect to compute, okay? You guys gonna ask for your tuition dollars back on Math 116? You only showed us how to solve 0% of the interesting problems. Can I get all my tuition money back? Okay, so here's the second fundamental theorem of calculus. It says every definite integral can be evaluated through antiderivatives. Of course, assuming you can find one, okay? It exists, but it's going to be hard to put your hands on it. And once again, what do I mean by that? Yes, little f has antiderivative capital F, but I maybe cannot produce it analytically. Okay. So here's what the theorem says. Suppose suppose little f on our interval AB to R has antiderivative capital F of x. Then little f of x is Riemann integrable. Moreover, the integral from a to b of little f of x dx is equal to f of x evaluated from a to b. And that symbol, big slash a to b, is by definition equal to the function evaluated at the top limit minus the function evaluated at the lower limit. Okay, so that's the second fundamental theorem of calculus. You give me any antiderivative, doesn't matter which one. That's because the constants cancel out. Constant here and a constant here cancels with the minus sign. Give me any antiderivative, and I do this integral by simply function evaluation. So that's the dream. To find that antiderivative, it reduces integration to function evaluation. That's the power. You'll see this written in several different ways. Integral a to b f prime of x dx equals f of x from a to b. Or you'll see integral okay, it's just using the, what was it, Leibniz notation, the df dx. Okay, it's the same thing as the prime, it's just the first derivative. All these are saying integration undoes differentiation. Integration undoes differentiation. And then sometimes, in more advanced books, you'll take the dx's and cancel them, and then write it as the integral of the increments of f of x, differential f of x, is equal to okay. They all mean the same thing. They're all saying integration inverts differentiation. First fundamental theorem, differentiation inverts integration. So they're inverse processes. Okay, it's pretty cool, actually. Okay, so it's 5:20, it's break. Max has a box full of goodies for us. I'll remind you that Project 2 is live. We've got it has 2 parts. Part 1 has been turned in by one person with a perfect score already. So that's looking good. So that means there are no mistakes in it for me. And it means, yeah, so some of you are getting a little bit of a head start. I think you're going to love it. It's all about optimization, and you're solving differential equations via optimization, though you won't see the differential equations unless you go looking for them. So look for it, post them. It'll be fun to see where you guys find them hiding, okay? But there are differential equations. There's a gymnast and a 10-meter platform diver, but you warm up on shooting basketballs and you get nice animations for all of them, okay? So when you get it right, you can tell, like a spec on the 10-meter diver is you have to do 2 flips and stick the landing. Whoa, okay? Cool, huh? So those are the kind of things that you don't get to do in a normal calculus course. We're abnormal and we're proud of it, okay? So let's take a few minutes. Okay, this is a reminder on the squeeze theorem. The squeeze theorem says, I have a really gnarly limit I'm trying to evaluate, and maybe the function is insanely complicated or I don't know enough about it, but I can bound it by 2 other functions. If those functions have a common limit at my point of interest, and one is an upper bound for the function that I'm really interested in, this squirrely guy, and the other one's a lower bound for it, then this common limit of the 2 easier limits to produce is the limit of the complicated function. That's the squeeze theorem. It's also called the sandwich theorem. Okay, so why do we care? Whoops, where'd it go? What happened? Oh, here it is. There we go.
In this video, we're going to prove...
Okay, let me get the volume going.
And everyone, thanks for joining us today. It's great to see so many of you.
Okay.
In this video, we're going to prove the fundamental theorem of calculus
Let me
at 3
turn
different
on
levels of
closed
rigor.
caption. There we go.
We'll discover the underlying intuition for why integrals and derivatives are opposites, as well as how that intuition relates to the rigorous proof of the theorem. As an added bonus, we'll learn about the importance of both formality and informality in understanding proofs.
Okay, so we're going to have 3 different proofs in 8 minutes, so it's 9 minutes. One is going to tell us why our brains are going to say we should believe this. The second one is going to attempt to start filling in some of the gaps of the first one. And the third one is going to be where, I think I could convince every person on the planet that this thing is true with the third proof, okay? I want to see how you guys react. You ready to react poorly or gaily, depending on, but just be honest, okay?
Started. This video assumes that you are familiar with the basic topics of calculus, and hopefully you've been exposed to the fundamental theorem already. However, let's review what it says for good measure. Let's first take a look at what this equation is actually saying. The integral on the left gives the area under a continuous curve f between a fixed lower bound and a variable upper bound. Because x is the only independent variable, we can rewrite this integral as a function, which we'll call a of x, with the a standing for area. Using this definition, the fundamental theorem looks much simpler and its meaning is clearer. It states that the rate of change of the area function at a given... Now you have this understanding about the fundamental theorem of calculus, and I encourage you to seek the same understanding for other theorems you come across.
What happened? I hit the wrong... Sorry about that.
Because x is the only independent variable is actually saying...
Come on. You're just writing
This
down a
video
of x.
assumes that you
There we go.
The integral on the left gives the area under a continuous curve f between a fixed lower bound and a variable upper bound. Because x is the only independent variable, we can rewrite this integral as a function, which we'll call a of x, with the a standing for area. Using this
There you go.
definition,
So,
the fundamental theorem looks much simpler.
differentiation
and its meaning is
undoes
clearer.
integration.
It
Is it
states
true?
that the rate of change of the area function at a given point is equal to the value of the curve f at that point. Let's see if we can understand what this means and why it's true.
So, level 1.
We begin by simply visualizing the area function. The input to this function, x, is how far across the page my hand is, and the function's output is the amount of blue ink I've used, or the total area under the curve up until x. Our goal is to find out how quickly the area grows as its upper bound increases. Notice that as I move my hand further to the right, the space between the x-axis and the curve is increasing. The larger this space is, the more ink it takes to keep up with the growth of the area function. Specifically, the amount...
Okay, so in this picture, we're adding up rectangles to get the area. What is the width of the rectangle here?
The tip of the marker.
Tip of the marker. Thank you. That's simple, okay? Now, when he has to draw farther, he's adding in more area with the same width. Okay? So his argument is going to be that the rate of change of area is the value of the function. Let's see if we are convinced by this. This is level 1, okay? So this is the junior high level, junior high proof, okay? Level 1. Let's just see are we convinced by that?
At a given point is equal to the distance between the x-axis and the curve f, which is, in turn, equal to the curve's height, f of x. This is exactly what the fundamental theorem says, completing our proof. The downside of this argument is that it's not very rigorous. It visually shows how the height of the function determines the area's rate of growth, but never once actually mentions the derivative. Let's see if we can make this proof more rigorous by applying the definition of the derivative, finding the difference in area for a small change in x.
Okay, level 2, high school,
We
okay?
begin proof 2 by changing x by a small amount, delta x, and visualizing the effect this has on a. We can examine the exact change in the area function, but we can also approximate it using a rectangle. These two regions have different areas, but as delta x gets smaller, the areas become closer and closer to each other.
So why is he replacing the area with a rectangle? You know, it's got that kind of a trapezoidal looking thing, okay? And he's replacing it with a rectangle. Why? Because that's the definition of the Riemann integral, okay? And now the delta x is not the width of the tip of the pen, because then you couldn't see his picture, okay? So this is a zoom, okay? So he's going to use the lower Riemann approximation. Remember we did the Archimedes approximation principle, which is really the squeeze theorem. You get the lower limit, you get the upper limit, and then when we would take both of them and they both finite and they agree, then that's the definition of the area. So he's using one of them here.
Let's estimate algebraically. Since the total area to the left of x plus delta x is equal to a of x plus delta x, and the area to the left of x is equal to a of x, the change in area is equal to the difference of these two values. Now we turn to the rectangle. Notice that it has a width of delta x and a height of f of x, so its area is equal to f of x times delta x. Once we divide both sides by delta x, the equation starts to look very familiar. Our final step is to take the limit as delta x approaches 0, which does two important things. First, it completes the definition of the derivative on the left-hand side, which allows us to rewrite it as a prime of x. Second, it turns the approximately equal sign into an equal sign, since the area of the rectangle becomes infinitely close to the actual difference in area. This proves the theorem.
Oops, come on. Back a tiny bit where it's no longer blurred.
Equal sign, since the area of the rectangle becomes infinitely close to the actual difference in area.
Okay. That's the second proof. So we use the definition of the Riemann-Darboux integral. We use the lower sum. We've got the definition of a derivative in there because we've got the area at x plus delta x minus the area of x divided by delta x. So it's rise over run. And we're approximating it by the Riemann lower sum here. That's what the rectangle is. We can see it's the lower sum here, not the upper sum. Okay. What's wrong with this proof? I mean, it's pretty good. Okay. Can you see any holes in it? Maybe you don't even need the third one because you guys are convinced, yeah?
Just an approximation.
Yeah, so, I mean, somehow, look at this. Yeah. So, this approximate, and then we just magically put limits on both sides and it became equal. Now, if I didn't say the word magic, you guys would say, oh, yeah, that's fine. That's how limits work. And it is, okay? And I'm sure I've done 2 or 3 proofs like that, derivations or reasons for why something works. I've done 2 or 3 like that for you, and you haven't walked out on me, okay? So it's not bad, okay? So now, level 3, the experienced college student proof. Let's see if you get it.
When I first saw this proof, it felt like the construction was pulled out of thin air to magically generate the desired formula. However, it is really just a way to clarify what the vertical line in proof 1 actually was, the limit of an increasingly thin rectangle. Examining this rectangle in proof 2 revealed that the difference in area divided by the difference in x approaches the height of the function, which is a more precise version of the claim we made in proof 1. However, proof 2 still contains a crucial step that is not fully justified. How do we know that the area of the rectangular approximation actually approaches the true difference in area? To answer that, we turn to proof 3. We begin with the same setup as proof 2, but take a closer look at the change in area. Instead of creating a single rectangular approximation using the height of f at x, let's create 2 rectangles, one using the minimum value of f between x and delta x, and one using the maximum value. We'll call the location of the minimum u and the location of the maximum v, so the 2 rectangles have a height of f of u and f of v, respectively. We know these values have to exist because of the extreme value theorem. There are now 3 ways to describe the difference in area, 2 approximate and 1 exact. The minimum height rectangle has an area of f of u times delta x, and the maximum height rectangle has an area of f of v times delta x.
Upper Riemann sum, lower Riemann sum.
We can describe the exact difference in area the same way we did for proof 2.
What we're trying to actually
a of x
compute.
Plus delta x minus a of x. The reason we created these rectangles is because they give us an upper and lower bound for the actual difference in area. F of u is always less than or equal to the curve f, as long as we're between x and x plus delta x. Likewise, f of v is always greater than or equal to f. Because of this, the actual area underneath f between x and x plus delta x has to be between the areas of these 2 rectangles, due to the comparison property of integrals. Let's write out our inequality and take the limit as delta x approaches 0, just like we did in proof 2. We'll also repeat the step of dividing all 3 expressions by delta x. In order to figure out what the left and right sides of this inequality approach, we need to examine u and v as delta x approaches 0. Since we defined u to be a value between x and x plus delta x, u gets squished between these two values as delta x gets smaller, and it ultimately approaches x. This means that we can replace our...
Okay. We're going to take limit as delta x goes of f of u. U depends upon delta x, because if I move delta x, for example, here, something much smaller, then u changes, okay? So u depends upon delta x. If f is continuous, which is what we're doing here, then we can take the limit inside the function. So f of the limit as delta x goes to 0 is of u of delta x is going to give us x. Okay, so u is trapped. So there's a squeeze theorem once here, the same for v. So we got the squeeze theorem to prove that the limit as delta x goes to 0 of u, which depends upon delta x, is equal to x, and the same for v. Okay, that's squeeze theorem once. This is our Archimedes approximation principle, lower bound, upper bound, which is the squeeze theorem again. Archimedes and the squeeze theorem. Two sides of the same coin, different sides of the same coin.
Applying the same logic for v, we have the value of 2 of the 3 limits in our inequality. Let's finally put everything together. Substituting in our values for the left and right limits, we see that the limit in the center is sandwiched between 2 limits that both approach f of x. Using the squeeze theorem one last time, we show that the limit must therefore be equal to f of x. It took many constructions, properties, and calculations, but we have proven the fundamental theorem of calculus beyond a shadow of a doubt. These 3 proofs each have their own advantages, since they all strike a different balance between intuition and rigor. However, the proofs aren't just different options to choose between. They actually support each other and work together to fully explain the ideas behind the theorem. More rigorous proofs allow for the hand-wavy, broad statements that make intuitive proofs possible. The level 3 proof justified our claim that the rectangular approximation in level 2 really does approach the true difference in area. And this rectangular approximation explained how our line in level 1 actually represented the rate of change of the area function. Without these rigorous proofs, we can't know what the simpler proofs mean precisely or why they work. Intuitive proofs also help us understand more complex ones. Knowing what the constructions in rigorous proofs represent on a simpler level aids immensely in following along. Intuitions also explain why mathematicians choose certain approaches over others. The approach of the level 3 proof, for example, would feel arbitrary if you weren't aware of the problems in the previous 2 proofs that the third was designed to solve. Truly understanding a theorem means knowing both the general reasons why it's true and also how to justify these broad claims. Now you have this understanding.
Anyway, that's just... So what do you think? Did you understand level 3? We did. We've done enough in the course that level 3 made total sense. Pretty much, okay? You have to go through it slowly and write it down yourself, perhaps, to be totally convinced, okay? But yeah, it's a pretty good proof. And it's, I think what I like about this video is, you see, when you're trying to prove something, it's much easier to prove if you know what you're trying to show, okay? Level 1 was getting you set up to discover what is the fundamental theorem of calculus. So you've got a statement now that you're trying to make precise why it's true. Level 2 was, man, I worked all weekend and I almost got it, okay? And you show it to your advisor and they go, that approximation sign, how did that become an equal sign, okay? And then you go home that night and you go, this big epiphany comes, epiphany, what's the word? Epiphany, thank you, epiphany happens. And you remember the squeeze theorem and you come back and say, oh yeah, That's how we defined Riemann integration in the first place. Okay, it's really important to use the squeeze theorem, and then it's all locked up. Okay, so that's how math is done. Okay, and then if you were to take Math 351 or Math 451, you'll do those proofs 3 or 4 a day. Okay, but you'll get better and better at understanding the intuition of how the proofs go. And, this is just one example. So, excited, not excited, excited, not excited, we don't know. I know. Watching that video took you away from my beautiful note writing. That's what really bothered you most, okay? You were in withdrawal of deciphering hieroglyphics, okay? That was the real issue. Okay, so once again, let's put our little table back here. So one person's function and derivative pair is another person's antiderivative and function pair. And most engineers carry this table in their head and nothing more. Okay, so let's take a quick look at these. I'll give you a hint of how to handle y absolute value of x is here. This allows the natural log to be defined for negative values of x, because we take x absolute value and make a positive. And there's no absolute value here. I'll give you a hint on that. Tangent to 1 plus tangent squared, that's just, once again, the quotient rule. Where does this one come from? Okay, and apply the chain rule. You guys are good with the chain rule, okay? So I'm going to say x is equal to tangent of arctangent of x. Why is it the chain rule? Because I've got a composition of functions. F of y is tangent of y, and g of x is arctangent of x. Okay? Let me call this star, and let me differentiate both sides of star. Okay, easy enough. Derivative of x, uno, okay, 1. Derivative of tangent, 1 plus tangent squared of y, evaluated at y equals arctangent of x. Well, I don't want it to look like a dot product, okay? Times the derivative of arctangent of x, okay? So that's what we're trying to find out, but we know now that when you multiply the derivative of arctangent of x times what's on the left, you get 1. What you have here is 1 equals, and when I plug in y equals arctangent of x into tangent of x, I get x. So this is 1 plus x squared times arctangent of x prime. And now it's just algebra. Okay, so that's how you get the derivatives of most of the inverse trig functions. You can use that to get the derivative of log of x from knowing the derivative of exponential of x is equal to itself. You can do, that's how you take functions and their inverses and calculate. Knowing one of them, you calculate the other. Okay? And the only trick is I could have written x equals arctangent of x of tangent of x, but that would have messed things up. You can see that the chain rule gets g prime of x on the outside, and that's what we wanted because we wanted to compute this one. Okay, so you can apply the same trick to getting the derivatives of arc cosine, arc sine, all of those other things, they come from the same way. So just homework if you want to. Calculate d by dx of arc sine of x. And you know the derivative of sine of x, so you can do sine of arc sine of x, okay? And then also show d by dx log of absolute value of x is 1 over x, no absolute value on the right-hand side. And here's the hint. Absolute value is x when x is positive, and it's minus x when x is negative. I know you know that, but you often don't write down all the things you know when you're trying to show something, and then it's just the chain rule because you know or you've done otherwise the derivative of log of x when x is positive, so now do absolute value of x when x is negative, and the chain rule will get rid of the minus sign for you. Okay, so just do this derivative when x is negative, and you'll be doing d by dx. Okay, and apply the chain rule to that. And remember, minus x in what we're doing is equal to absolute value of x when x is negative. So when you apply the chain rule, it's all going to work out. Okay? So this allows us to establish all of our antiderivative formulas that we have here. I'm going to get some extra power here. Where'd you go? There we go. So that's the table you want, and then what we're going to show you is this plus simple substitution rules, etc. Okay. First fundamental theorem of calculus, every continuous function has an antiderivative. Second fundamental theorem of calculus, every definite integral can be evaluated via antiderivatives. So let's practice that a little bit. Sorry. Second fundamental theorem of calculus. And then recall our notation that if we take any function and we do this evaluate symbol, that's by definition f of the upper limit minus f of the lower limit. So it's a really useful and powerful notation. Okay. So let's compute the integral from 0 to 5 of 2x cubed plus e to the x dx. So if we're doing it via antiderivatives, what do we have to do? We find an antiderivative of the monomial. So we raise to the power and divide by the power. The antiderivative of e to the x is e to the x. Then we evaluate this from 0 to 5. And so we get a half, 5 to the 4th, 625 plus e to the 5th minus 0 plus 1. Okay, so it's just arithmetic. And the beauty of antiderivatives, when you can find them, is it really does reduce it to just function evaluations. Okay? Function, 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 function. They're related by derivative of these or these, and then second fundamental theorem of calculus, evaluated, you're done. So it's really sweet when it works. Let's do another one. Limit from integral from 1 to e, 1 over x plus 1 over 1 plus x squared dx. How do we do it? We need to find antiderivatives. Antiderivative of 1 over x log of absolute value of x. Antiderivative of 1 over 1 plus x squared, that's arctangent of x. And then we do function evaluation. In here, I'm just going to write arithmetic, because you guys can plug it in as well as I can. Okay, e is positive, so the absolute value of e is just e, and the log of e is 1, etc. Okay, so when I plug in 1, absolute value 1 is 1, log of 1 is 0. Just arithmetic, function evaluation. So that's the beauty. Okay, let's do this one. X over 1 plus x squared dx equals. So what's the antiderivative of x over 1 plus x squared? Let's go back to our table. X over 1 plus x squared. And we look, and we look, and we look, and it's not in there. Darn it. Okay. Okay, so it's not in our table. No antiderivative in our table. Okay. So, just like we had rules for differentiating products of functions and function compositions and ratios of functions, we have methods for finding antiderivatives for products of functions, ratios of functions, and compositions of functions. So that's where all of these things that you guys were taught come in. Okay, so I'm going to call this the art of the antiderivative. By inverting differentiation rules. And why would we invert differentiation rules? Well, because we know that integration is the inverse of differentiation. So the first one is almost too easy, the power rule. d by dx of x to the k plus 1 is equal to k plus 1 x to the k. And this is true for all real values of x and non-negative integers 0, 1, 2. So what does this say? It says that the antiderivative of x to the k is x to the k plus 1 divided by k plus 1. Antiderivative x to the k dx Okay, how do we prove it's an antiderivative? We differentiate it and we get the function back. Similarly, integral x to the alpha antiderivative is x to the alpha plus 1 over alpha plus 1. Well, I should have written a constant here. My apologies. Okay, this is for x positive alphas in the reals, alpha not equal to -1. Why not equal to -1? Because we don't want to divide by 0. Okay, so find an antiderivative for 3 times the square root of x. Everybody got a plan of attack in mind? Square root of x is x to power a half, right? So antiderivative, 3 square roots of x dx. Antiderivative is, so it's 3x to the 1/2 plus 1 over 1/2 plus 1 plus a constant. And so that's 3x to the 3/2 over 3/2. And then you can, whoops, not that one. And you get 2x to the 3/2 plus a constant. Okay, so that's how the power rule, super nice when it's there working for you. Did I call that A? Yeah, I did, yay. B. Fundamental rule. It says the antiderivative of f prime of x dx is equal to f of x plus c. Okay, that's the second fundamental theorem of calculus. And so if we recognize the integrand as the derivative of a known function, then it's game over, okay? It's done. Example, integral 1 over 1 plus x squared dx. We recognize this as the derivative of the arctangent function because it's in our little bitty table that we have uploaded to our little bitty engineering brains, okay? So we've got these 7 or 8 antiderivatives that we've uploaded to our organic brain, and we look for those, and when you see them, done, game over. Okay, so the first one, power rules, the fundamental rule. It's not easy to recognize the integrand as the derivative of something, but when it happens, don't look a gift horse in the mouth, okay? So that's what that one says. C. Inverting the chain rule by U substitution. Anybody know why it's called U substitution? Because there's a U in the word substitution? Good or no? It's simply because mathematicians commonly use U as a change of variable. It's all it is, okay? When I was growing up, we didn't call it U substitution, at least not at Oklahoma State, okay? And once I got beyond undergrad, I never did another U substitution until I taught college courses, okay? And all the time, all of the patents I have at Ford Motor Company, et cetera, I've never done a U substitution, but they show up a lot, okay? So, if inverting the chain rule, how does that go? Chain rule says d by dx f of g of x equals f prime at g of x times g prime of x. So, issue is that, yes, if I go into this thing and I identify for you f prime and g prime, then you go, yeah, that's f composed with g plus a constant, okay? So this can be hard to recognize. So this is where the change of variable comes in. We let u equals g of x so that du by dx equals g prime of x. So I'm mixing deliberately, I'm deliberately mixing the notations here. Because if I do du dx times dx, that's just g prime of x dx. And you've learned what we do here. We cancel the dx's. So the differential in the u variable is equal to g prime of x dx. So that's really important. Okay, so I've got this. So this is f prime of u. This is du. So that's why u substitution is so nice. And now we just apply the fundamental rule. Whenever I integrate a differentiated function, I just get the function back. But u is g of x plus c. And we'll do one example and then we stop. So we motivated by finding an antiderivative for this friendly amendment to the arctangent. Okay, so the u substitution is to let u of x equals 1 plus x squared, and then du is the derivative of 1 plus x squared, 2x, times dx. And so this becomes 1 over u du. X dx is du. 1 over 1 plus x squared is 1 plus 1 over u. And so that's logarithm absolute value of u plus a constant. And then u is 1 plus x squared. And since 1 plus x squared is always positive, we can get rid of the absolute value sign. So that's u substitution. Okay, we'll do a warm-up when we come back. Now, I've shown you 3 different methods. We've got a couple more. What do you think I mean by the art of the antiderivative? Why is it an art? Well, things are kind of artisanal when there's not a recipe that you can apply ahead of time to know exactly what to do. So, has everybody in the room played basketball at least once? It's pretty international and non-gender specific and everything. In fact, the most famous basketball player in the world is now Caitlin Clark. Okay? How do you know when to drive for the hoop and make a layup versus stop and make a mid-range jumper or go crazy and shoot and go for 3? How do you know when to do that? Exactly.